Let's begin with the third and last part of the descriptive chemistry unit. We will see VSEPR theory and molecular geometry, multiple and single bonds, intermolecular forces, bonds order, Le Chatelier principle, and to finish off, equilibrium constants and expressions and the definition of activity. Some aspects of three-dimension configuration cannot only be explained by Lewis structures and resonance shapes. Because of this, we will move a step further and talk about the valence shell electron pair repulsion theory, which will allow us to explain the molecular structure. We will know, for example, how to understand the structure of the molecules in the slide water and methane. This theory is based on Lewis structures and says that for minimizing the repulsions between atoms in a molecule, electron pairs must be placed as apart in space as possible, considering the three dimensions. If two electron pairs are not bonded as lone pairs, the repulsion between them is much higher than if they both were bonded. In the middle of the strength scale, we have the repulsion between one lone pair and one bonded pair. This explains molecule structures, distances and bond angles and bond energies valences. Once we have the theory, we can move to how to represent a molecular geometry. First, we have to do its Lewis structure. The second step is to find the steric number of the central atom, which is the sum of the number of atoms bonded at the central plus the number of lone pairs. Then, depending on the steric number value, we will know the certain disposition of the electron pairs around the central atom. We must differentiate between the electronic geometry, the one defined only by the steric number value, and the molecular geometry, which depends on the atoms bonded to the central one. To know the molecular geometry, we must introduce the VSEPR notation. A will be the central atom, X or B will be the number of terminal atoms, and E will be the number of lone pairs. In the examples, we can see that the three molecules have tetrahedral electronic geometry, but the number of terminal atoms and lone pairs is different, which changes completely the molecular geometry. Now you will see some examples of different geometries. With steric number 2, 3 and 4, steric number 5, and finally steric number 6. Moreover, the lone pairs condition the molecular structure because the angles reduce by the repulsion of the clouds of electrons. When two atoms have different electronegativity, the structure is also affected because electronegative bond pairs take less space than electropositive ones. Apart from that, multiple bonds take more space than simple ones. Now, let's move to multiple and single covalent bonds. First, we are going to talk about single bonds, which are in fact sigma bonds. This type of bond is the strongest among the covalent ones, and it is the first to form between two atoms. Frontal orbitals overlap with respect to the internuclear axis, and they can move and rotate freely without breaking any bonds. All types of orbitals can generate sigma bonds, but in F orbitals this is not usual because as they are very deep in the atom, they don't participate in bonding. Here you have an example of a molecule that has sigma bonds, methane. The other type are the pi bonds, which are present in multiple bonds. Lateral parallel atomic orbitals overlap both above and below the plane of the atoms, and this restricts their rotation because otherwise the bond would break. A multiple bond is always a combination of one sigma and one or two pi bonds, depending on if it is double or triple. For every pi bond formed, there has to be one p orbital without hybridization, also called a pure orbital. Therefore, atoms with multiple bonds will never have a sp3 hybridization. Moreover, s orbitals are not able to form pi bonds, as they are spherical and symmetric from all sides, therefore can't do a parallel overlap. Here you have an example of a molecule with a double bond, ethylene, which has a combination of a sigma and a pi bond. And here, a molecule with a triple bond, acetylene, with one sigma and two pi bonds.
Let's start with a different topic, which is intermolecular forces. This slide shows us the van der Waals interactions. The van der Waals can be found between nonpolar molecules and polar molecules. As for nonpolar molecules, it can either be an instant dipole, which means that the electrons move into an orbit producing a bias, and an induced dipole, which means that the electrons move in response to an external polarization, and an interaction dipole-dipole, which are both induced, and it can also be called London forces. As for the polar molecules, we can either have a permanent dipole or an interaction dipole-dipole that is permanent. Now, what is the relation between the van der Waals forces and physics properties? These van der Waals increase with the atomic number and therefore with the molecular mass, and they also depend on the form of the molecules. These van der Waals forces have an influence on physical properties. This means that the attraction between the molecules increases. Let's do an example. Let's compare the polarity of the different molecules and indicate the nature of the intermolecular interactions present in each case. Now, for intermolecular interactions, we understand that the hydrogen bonds are the strongest, and the dipole-induced interactions, or also known as London forces, are the weakest kind of interactions. For this example, we have 4 different molecules: carbon tetrachloride, dichloromethane, methane, and chlorhydric acid. For the first molecule, which is carbon tetrachloride, we have a hybridation of the carbon, which is sp3, right? In this case, we have a polar molecule, which is dipole-dipole induced. The second molecule will be the dichloromethane, which also has a hybridation of the carbon of sp3. In this case, though, it is non-polar. It is formed between a dipole which is permanent, a dipole that is not permanent. But the strength that pulls each of the sides is not equal, because not all the molecules that are bonded to the carbon are the same. We have 2 hydrogens and 2 chlorides, right? For the methane, which is also sp3, we have a polar bond. It is dipole-induced, and the strength is exactly the same. Why? Because the 4 atoms bonded to the carbon are exactly the same. In this case, hydrogen. It would be the same thing, the hydrogen, as the chloride. Any molecule or any atom would work and would make a polar bond. As for the chlorhydric acid, it's non-polar. That meaning that the atoms are not pulled exactly the same. So one atom has more strength than the other one, and the electrons go that way. As for the next example, we have only 2 real molecules, which is chlorine and tetrafluoromethane. Chlorine is a polar molecule because both sides are formed by the same molecule, so they make the same strength and they pull just as strongly. Now for tetrafluoromethane, it is also a polar molecule. Why? Because we have a carbon in the center bonded to 4 different fluorides. In the next 2 slides, you can see some more examples, which are all about the same. Let's have a look at the bond order, bond length, and bond strength. For bond order, it will be 1, 2, 3 for simple, double, and triple bonds. And there's a fraction if there is resonance. Higher bond order mean shorter bonds or stronger bonds. Now let's see an example. If we have, it doesn't even matter what molecule we just have to look at the bond between 2 atoms. Now, a triple bond is always the shortest and strongest. You have to picture as if it were to be closer and tighter, right? The double bond is found in between the triple and the simple bond, and then the simple bond is the longest and weakest. That means it's easier to undo. Let's have a look at this second example. We have acetic acid and acetate. For acetic acid, if we have a look at the bond, at the simple bond between the carbon and the oxygen, as we've mentioned before, because it's a simple bond, it will be the longest and weakest. Because in this molecule, we don't have a triple bond, the double bond between the oxygen and the carbon would be the shortest and strongest, right? As for the acetate, if we have a resonance, they have the same length and the same strength. When we take the resonance into consideration, the more atoms involved in the resonance, the shorter and stronger this resonance is.
Now let's move to a very different topic, which is Le Chatelier principle. This tries to explain how an equilibrium will be modified if we change their conditions. The system will always try to compensate the change by shifting to products or to reactants. If we increase the concentration of reactants, for example, the equilibrium will shift to products to use up the new substance. This is the same that would happen if we lowered the concentration of products. If we did the opposite and we increased the concentration of products, equilibrium would shift to the other side. If we change the temperature, the effect will depend on if the reaction is exothermic, it produces heat, or endothermic, that it absorbs heat. If we increase the temperature in the first case, the equilibrium will shift to reactants because we treat heat as if it was a product and we increased its concentration. In the second case, it will happen just the opposite. Don't forget that the equilibrium constant always changes with the temperature. Finally, if we increase the pressure of a reaction, for example, which is the same as decreasing its volume, to try to compensate the change, the equilibrium will decrease the number of gaseous molecules. Solid and liquid ones will not be taken in consideration, as they don't affect in the pressure of the system. Therefore, the reaction will move to the side of the reaction with less moles of gas. Now let's consider the following equilibrium as an example. We have hydrogen peroxide, which gives us hydrogen and oxygen in equilibrium, and the reaction is endothermic because it needs energy to produce. Now, think about what will happen in each one of the following cases. If more hydrogen is added, the equilibrium will move to the left, to reactants, to use up all the hydrogen that has been added. If the oxygen is removed, the reaction will move to the right, to products, to restore all the oxygen that has been eliminated. What happens when we increase the temperature? As it is an endothermic reaction, the equilibrium will move to products, because we treat heat as a reactant. Finally, if we reduce the volume, the reaction will move to the left, because it is where there are less moles of gas in the reaction. The last topic of this unit is about equilibrium constants. There are two types of them, experimental and thermodynamic constants. The first type has units which depend on the products and reactants of the reaction and their own units, and also the stoichiometric coefficients. Kc is about concentration equilibriums, and Kp gives an equilibrium constant for its partial pressures. The second type are the thermodynamic constants. We need to define a reference state for them, which is usually 1 mole per liter in solutions and 1 bar for gases. Let's explain more about the thermodynamic constants. The terms in them are just quotients between the concentration or pressure in the system divided by the one in the reference state, and therefore the units cancel each other, and the final constant K is dimensionless with no units. This quotient can also be called chemical activity. As we just explained, it is the quotient of the effective concentration in the system divided by the one in the reference state. In gases, this effective concentration is just the pressure in bars, and in solution, the concentration expressed in moles per liter. In solids and liquids, the activity is always 1, because the concentration in the system coincides with the one in the reference state. To finish this topic, we will see what happens when we combine two or more chemical reactions. If we sum them, the final constant will be the product of the constants of each reaction. If we, on the contrary, subtract them, the constants will have to be divided. Take into consideration that if we know the logarithms of each constant, we can just sum or subtract them to find the logarithm of the final reaction, which in some cases is so much easier. This is the end of the descriptive chemistry unit. Thank you very much for your attention.